Hello, everybody. We are going to solve problem number 2, chapter 4 today. Problem number 2 basically is titled Line Speed. It's about the manufacturing process and assembly line speed and the number of defectives. So basically, we want to know what is the relationship between two variables, line speed, which is foot per minute, and number of defective parts found, which is basically a count, a number. We want to know basically the relationship between the two, and we want to quantify the relationship. These are the data sets, 6 observations. We want to basically for the first part, we want to develop a scatter chart with line speed as the independent variable and number of defective parts as dependent variable. I want to know if the higher speed basically improves, decreases or increases the number of defective parts. So let's start with part A. So I have my data set available over here. What I do, I can select data, choose chart, scatter chart, and mark the scatter chart. And as I can see, line speed is basically appear as my horizontal axis, my x-axis, and number of defect products basically appears in the y-axis. I can change it. I can do the right click, select data again. In the x-axis is if I decide to have number of defective parts found, I can select this one over here, and I can come back in y-axis and select line speed. I can do OK, and then I have this data over here. I can do many things actually. I can, by selecting on the data points and doing the right hand side, you can add trend line, which basically adjust the trend line. If you remember, we did least square method to basically find this trend line, and it's easily can find it for us in Microsoft Excel. You can even display the equation on the chart and also the R square, and it's easily can be shown over here. As you can see, we can nicely get R square and equation line for this equation over here. The relationship is negative. The higher values of x basically indicates lower values of line speed. So basically, as the line speed increases, we have now I'm going to solve this problem using Microsoft Excel. This is Excel 2016, and that was why actually this one was a little delayed. As you can see, it has data analysis and solver in the data ribbon. You can also go to, in fact, tools and add add-ins, in fact, and then add these two. So you need these two icons for your data analysis. What I do, so there are formulas, we have review, we have data, a different icons. So I go to data analysis, and in data analysis, I pick a regression, right? And in the regression, I have to use the Y input. So basically, I choose the Y input over here. Y is the dependent variable, and I can use the line speed as independent variable, X input X range. So there are some options like constant to 0 that we don't want to do that. The confidence level, we can basically do the 95%, or if we don't do it, reports 95 and 99, so we just leave it like that. So we have different options. Output action, whether you want to basically report it in a new worksheet, or I put it in the new worksheet play. Basically, it opens a new worksheet for me. Um, and if you have any restrictions on number of residuals, basically we can report it, residuals, standard residuals, line fit plot, and stuff like that. I hit OK, and it basically gives me the report for it gives me the report for the regression analysis. So what we have over here is the summary output. We have the R square. R square is 0.7391, and this is the x variable and the intercept. Basically, we can rename it as well, but the x variable is the coefficients are 22.17, and also the x variable is negative 0.14 with this standard error. So basically, how it looked like is y equal 22.17 minus 0.147 times x. That's how the relationship look like. So I write it down over here. So it would be y equal to, and that's how I sometimes expect it from you, 17. So as you can see, the coefficient is negative, so I put negative 0.147 times x. So that's how this relationship looked like, for example, for part A, and that we can basically use this coefficient. Some characteristics, f is greater than 10 means that the model is valid. These are the degrees of freedom, 1, 4, and 5. We have a total of 5 observations because the data had basically 6 observations. So basically, this is n minus 1, the total degrees of freedom. The answer for part C, we want to know 0.01 level of significance. Test each of the regression parameters beta 0 and beta 1 is equal to 0 at the 0.01 level of significance. So we go over here, basically this is part B, and part C is 0.01 level of significance. We have to compare with p-value. So we look at x variable. The p-value is equal to 0.028, right? So that's the p-value. Here is the deal. If p-value is greater than alpha, which is the significance level, which is over here 0.01. So what happened over here, we do not reject the null hypothesis. In this case, we do not reject the null hypothesis. That is, in fact, beta 1 is equal to 0. That's the null hypothesis. In our case, p-value, which is 0.02, is greater than 0.01. I'm sorry, I did it wrong. Therefore, we cannot reject the hypothesis that beta 1, or let's just put it b1 as well, put it over here, is equal to 0. We cannot reject that. So basically, beta 1 is kind of 0. All right? In which case, we would say there is no relationship, in fact, between the line speed and the number of defects. So that's the answer. So at 0.01 level of significance, there is no relationship. So we cannot say the relationship is that strong. However, if we change this 0.01 to 0.05, then we are able to find the relationship. So in part C, if alpha was equal to 0.05, then, 0.05, then we cannot, basically, we reject the hypothesis that beta 1 equal to 0, means that we accept the relationship between the two. So that's the hypothesis test for part C. Over here, the interpretation of the intercept is kind of irrelevant. And the reason why is that because we did it with interpolation in calculation of the beta 1 and beta 0, therefore the interpretation of p-value is irrelevant, so we don't basically consider that. That was part C, and then let's take a look at part D. In part D of the problem, it says that how much of the variation in the number of defective parts found for the sample data does the model you estimated in part P explain? And as you can guess, that's related to the R square, which is 0.739, so about 43%, about 74% of the variation is being explained by the independent variable. In fact, it's better to say the variation of dependent variable is been explained by the independent variable. So by this much, basically we can say that this problem is solved. I put also a complete solution of the problem online, so you can take a look at it. Thank you.